Hello everyone, this is the second lesson on double integrals, so sections 4.1 and 4.2 is what we'll be covering. So first, a quick review of what we did on last Wednesday's lesson. So remember our setup for doing double integrals. We start with a multivariable function, f of xy, and I'd like for you to think about f of xy as being a density function. That it represents the density of something per unit area. So maybe something like people per square mile was our example last class, or maybe biomass density per square mile, or some kind of density per unit area. And sort of the second component is that we need a region, capital R, in the plane, in R2. Which I'll go ahead and draw here on the side. So then I'll write the double integral like this. The double integral over the region R of f of xy dA. And I'll write what this says in notation first, and then I'll sort of explain what the notation means, more like as a process. So it's the limit as delta x and delta y go to 0 of the sum over all the boxes, which I'll explain in a moment, of f of xy times delta a. So again, I don't need you to necessarily think about each of the pieces of this notation. I want you to think more about the process that it represents. First, imagine slicing R up into little mini boxes, as we did last class. Then the second step is to approximate whatever you're trying to approximate box by box. The way I want you to think about this is think about taking f of xy times delta a, where delta a is the area of each one of those little mini boxes. So again, we're going to multiply the value of the function on a specific box times the area of that box for each one of those boxes. And then I'm going to add up the results of those, and then I'll take a limit as the dimensions of the box approach 0. And the result of this process, for thinking about f of xy as a density function per unit area, think of the result, the double integral, as representing the total of whatever it was on the region R. So if f of xy was density of people per square mile, then the double integral of f over the region R would be the total number of people on the region R. So this is a quick summary of what we saw on last Wednesday's class. And what I'd like you to do is take a few minutes right now to open up lecture problems number 20 and try the first 3 problems, numbers 1, 2, and 3 from that PDF. I have a second part to this video that is supposed to come after you've attempted those. I'll talk a little bit about those problems and then go on to our continuation of this lesson after that. So take a few minutes, take maybe 10 or 15 minutes to get started on problems 1 through 3. Make as much progress as you can. If you get stuck, I'll do a little bit of explaining of some of those problems in the next video. Okay, so at this point, I'm hoping that you've already attempted problems 1 through 3 from lecture problems 20. If you haven't, let me just give you a quick preview of them, and then you can give them a try before watching the rest of the video. The first set of problems asks you to think about the same region R in the plane that I've described here, and you're supposed to tell me whether these double integrals are positive, negative, or 0 without actually trying to calculate them. You haven't learned how to calculate these yet. But just based on the definition, based on the process that we've learned, can you tell me at least if they're positive, negative, or 0? So you can see the region is the same for each of them, but the function is different. In this next problem, I want you to just give me a rough estimate, again, based on, not on trying to actually calculate anything, but just based on the definition that we talked about. And then finally, we did learn how to calculate double integrals over rectangles at the end of last class, so give that a try on this problem. So if you haven't tried these yet, go ahead and try them now. I will pause for a moment, and then I'll go back and review parts of these problems with us together. So now that you've attempted these problems, I'm going to talk through some of the solutions and then go on to some of the new material. Since we don't yet know how to calculate these integrals exactly, what we'll do instead is see if we can apply the definition in terms of this process of slicing, approximating on each slice, and then summing and limiting to at least decide whether these double integrals are going to be positive, negative, or zero. So we'll start by first slicing the region into little boxes. Next, I'll imagine what happens if I multiply the value of the function f of xy times the area of each box on each one of these boxes. So since the function f of xy is x cubed, I'll just be doing x cubed times the area of the box times delta a. Now the thing that I can notice here is that that function x cubed is always negative on the points inside my region. So if I'm looking at the region here, all of these points have negative x values, and so if I calculate x cubed at any one of the points inside of R, inside of any one of these boxes, I should get a negative number. So that means this x cubed is always going to be negative, and I'll be multiplying it by delta A, which is always a positive area. So I'm multiplying a negative number times a positive number for each one of those boxes. So since my calculation on each box gives me a negative number, that negative x cubed times the positive area, when I add up all of those results in the sum, I'll be adding up a whole bunch of negative numbers. And so the sum itself must be negative. Now I can also take the limit, but if I'm taking the limit of a bunch of negatives, I'm going to still be getting a negative number. So in the end, this double integral must be equal to a negative number. So even without calculating anything, just by thinking about this process and thinking especially about this step where I am estimating the value of the function times delta A on each box, I can at least decide whether my double integral is going to be positive, negative, or zero. I'll try approaching this next problem in sort of the same way. So I'll start by slicing the region into mini boxes. And now I'll try to approximate f of xy times delta A on each one of those boxes, or think about what it would be equal to, at least whether it's positive, negative, or zero. Now, my function here is y cubed, so I'm doing y cubed times delta A. That is y cubed times the area of each of these boxes. Now, if I look at the boxes here, sometimes y is positive and sometimes y is negative. It depends on the box. And in fact, that means y cubed will sometimes be positive and sometimes be negative. And if I think about it, since y cubed is an odd function, the value of y cubed times the area of the box should cancel out for a box on the top with a box on the bottom. Again, because it's an odd function, these y cubed times delta a's ought to cancel out. Or maybe a better way to say it is, for some of these boxes, y cubed times delta a is positive. For other boxes, it's going to be negative. And then once I go ahead to sum, the positives are going to cancel out with the negatives. And so my sum is going to be 0. And if I'm taking the limit of a bunch of zeros, then I'm still going to be getting 0. I'll sort of quickly talk through this last one, but the main thing that I want to notice here is that my function e to the x is always positive. At any point inside of R, I'm getting a positive number. And so whenever I do e to the x times delta a, that is that f of xy times delta a piece, I'm always going to be getting a positive number times the area, so still positive. And so when I sum those things up, I'm going to get a positive number, and then taking the limit, it'll still be positive. Okay, now here's another problem, and I'm going to talk about this problem in a little bit different way, just to remind you of something we did last time. And that was using double integrals for average values of a function. So remember that the average value of f on the region R is 1 over the area of R times the double integral of f over the region R. Now, sort of just by eyeballing this function, you can see that the function is equal to about 200 all over the region R. And so I can see that this average value is about 200. So now I can really just sort of set up an equation here. I say 200 is approximately equal to 1 over the area of R times that double integral. And remember, the double integral is what I'm trying to solve for here. Now, since this is just a disk, the area is easy to calculate. I can see that the area is equal to pi r squared, so pi times 3 squared. And then I can just go ahead and solve for the double integral. I'll give us another way of looking at this, this time sort of in terms of the process of the definition of double integrals. So if I start by slicing the region up into little boxes as usual, and then go ahead and think about approximating f of x, y times delta a on each box, I realize that I'm basically always calculating something like, well, f of x, y is always close to 200, so this is always about 200 times delta a. And so for each box, I'm calculating 200 times the area of the box. And if I think about adding these things up, I'm really adding up 200 times delta A for each one of those boxes, but I can factor out the 200 here. And so it's really 200 times, well, 1 times the area of the box. So really 200 times the sum of all those little areas, which really would just be the area. If I'm adding up the areas of all the boxes, I should just get the total area. So this is 200 times the area of the region. And then that last step of limiting doesn't really do a whole lot since I'm just taking the limit of a constant. So I really do still get the 1800 pi. Okay, now the last problem that you're supposed to work on. This one is reminding you of how to actually calculate a double integral when the region is a rectangle. So first, a reminder about this rectangle notation. This isn't a cross product. What I'm doing is telling you the range of x's and the range of y's when I write it this way. Always the x's first and then the y's. So this is a way of describing rectangles, and I'll just draw the rectangle for you here so it's clear what I mean. I want x to range from 0 to 1 and y to range from 0 to pi. So I'll just go ahead and draw that rectangle for us here. So x goes from 0 to 1, y goes from 0 to pi. So now remember, the way to calculate these things is to use what's called Fubini's theorem. And Fubini's theorem says that we can take this double integral, which we hadn't learned how to calculate before we learned Fubini's theorem, and instead turn it into an iterated integral. So I'm going to write that double integral down one more time, and I'm going to change it into an iterated integral, that is an integral of an integral. And here's what Fubini's theorem sort of tells us. We can write down the range of x's and write that as an integral over x, and then write down the range of y's and write that as an integral of y, and it's just the integral of x of the integral of y. So now the key to calculating the expression on the right is to remember that inside those red parentheses, we should treat x as a constant. And I'm going to write this almost every time that we have an iterated integral, because I think it helps explain a lot of what we end up doing. So in this next step, I'm only going to be working on what's inside the red parentheses. I'm going to leave everything on the outside alone, and I'm going to be treating x as a constant. So that integral that I'm doing, you can really think about with fundamental theorem of calculus, I'll be doing a partial antiderivative, treating x as a constant and doing the antiderivative only with respect to y. So I'll leave alone what's on the outside and just work what was inside the parentheses. So I'm treating that x squared as a constant, so it's just a constant factor, and taking the antiderivative of sine y, which would be negative cosine of y. So you can see x squared was a constant factor, so I just left it alone there. Now the e to the x is also a constant, but it plays a different role here. Remember, the antiderivative of a constant c would just be c times y. And so since e to the x is just treated as a constant, It's just that constant times y. And now, as usual with fundamental theorem of calculus, I'll go ahead and plug in my limits of integration for y. So y equals 0 to y equals pi. Okay, so now let me go ahead and carefully plug in y equals pi, plug in y equals 0, and subtract. Okay, so you can notice I was careful to just keep the x's as x's and only plug in for y's. Now you can see the first part I plugged in y equals pi, second part I plugged in y equals 0 and just subtracted. Let me go ahead and simplify this a little bit, but you can notice that the expression that I'm left with doesn't have any y's left. I integrated all the y's away. So I'm going to have an expression now just with x's in it. So it ends up being 2x squared, plus pi times e to the x. And I'll integrate that dx. And now it's a single variable calculus problem. I can just integrate this function with respect to x, do this definite integral. So again, I use fundamental theorem of calculus, take the antiderivative of this expression, and then I'll go ahead and plug in x equals 0, x equals 1, and subtract. So you can see that I broke this double integral problem down into two single variable integrals, and that's what enabled us to solve the problem. Fubini's theorem says you can turn, at least over a rectangle, turn a double integral into what we're calling an iterated integral, an integral of an integral. And in fact, Fubini's theorem says you can do this in either order. So let me just show you what the integral would look like if I did it in the other order. This one I did x on the outside, y on the inside. Let me just write it down in the other order so you can see. I could have done y going from 0 to pi on the outside, and then x going from 0 to 1 on the inside. And I'll just write that same function down. And I won't go through it, but I could have evaluated the whole thing in this order, integrated with respect to x first on the inside and then y, and I should get the same result. Fubini's theorem says that I should get the same thing in either order. So Fubini's theorem tells us how to do double integrals over rectangles, but there's a natural question. How do you calculate double integrals over regions that aren't rectangles? How to calculate double integrals over non-rectangles? And that's what we'll sort of be spending the rest of today on. Okay, so here's a new problem where I've described a new region R for us, and we're supposed to calculate this double integral. So I'm going to rewrite the region R using inequalities. So I know that y has to be greater than or equal to 0. I can see that because we're above the x-axis, right? So that sort of symbolizes this bottom edge to the triangle. Now I can also see that x is going to be less than or equal to 1 because of that right-hand side of the triangle. That sort of symbolizes this edge of the triangle. And then finally, the other edge, I can say y is less than or equal to 2x. We saw that it's bounded by the line y equals 2x, and since we're below that line, that's why it's y is less than or equal to 2x. So once again, we know how to think about this. We can imagine that cosine of x plus y as being some kind of density function per unit area, and R as being the region, and then this double integral represents slicing, approximating on each slice, adding up the results, and taking a limit. But again, we don't really know how to calculate this yet, although we can still use Fubini's theorem, but kind of being careful about the region that we're working with and the fact that it's not a rectangle. So let's see how that's going to work. So setting up Fubini's theorem, the way that we normally would, we would say that, okay, this double integral ought to be equal to the integral of an integral. So I'll say it's an integral with respect to x of an integral with respect to y of this function cosine of x plus y. Now, one thing to notice is that the function stays the same. The density function is not affected by this process. So think of there being really two elements to these problems. First, there's the function, the density function, and second of all, there's the region R. The function is not what makes this problem harder than the rectangle problem. The thing that makes it harder is that the region R is different. And so that's what we're going to have to think about how to adapt to. Now, the way that I think of these kind of problems when we're setting up our Fubini's theorem iterated integral is that we sort of have four blanks to fill in. That is the upper and lower limits of integration for both x and y. Now, as always, the way that we think about this is to imagine that inside this parentheses, x is constant. And what that lets us do is to say that the limits of integration for y, the bounds for the y integral, can depend on x. You can have expressions involving x in the limits of integration for y. And that's how we're going to account for the fact that R is not a rectangle. Now, if we're thinking about x as being a constant, let me try and draw that in our picture on the left. So you can see I've fixed a value for x. I'm thinking of x as a constant. I'm picking a constant between 0 and 1 because that's sort of the part that's relevant here. Now, once I've fixed that value for x, let's think about the range of y's that are allowed. In particular, what's the lower limit for y once I've fixed that x, and what's the upper limit for y? I've drawn a vertical line because I'm setting x equal to a constant. So that equation, x equals a constant, gives me a vertical line. And I'm looking at the line segment that's actually inside of the region that we care about. So the lower limit, the smallest that y can be along that line segment, is always going to be 0. It sort of didn't matter what x I chose. The lower limit for y was always going to be 0. And so I'll go ahead and plug that in for my lower limit for y. Now for the upper limit, you can see that the upper limit depends on what x is. For x is close to 1, we're going to have larger upper limits than for x is close to 0. We'd have lower upper limits. But we can figure out what that upper limit is as a function of x, right? This line segment on top is given by the equation y equals 2x, and so that upper limit will be y equals 2x. The largest that y can be is what it is along that line, y equals 2x. So y equals 2x would be the upper limit of integration. Now it's a little bit odd to be putting an expression with x's into your limit of integration. However, again, because we're treating x as constant in these parentheses, it's okay. This 2x is really being treated as just a number. It's being treated as a constant inside this inner integral. Now, by contrast, on the outer integral, we're not going to be treating anything as constant. We can't make any claim like that. And so these limits of integration have to just be numbers. They have to just be constants. And that, in fact, kind of makes our life easier. What's the upper limit for x and the lower limit for x within this region as numbers? Well, x can't be any smaller than 0, and it can't be any greater than 1. And so I'm just going to write 0 to 1 for x. Let's see how the algebra works out here once we give this a try. I'll write this out again, and I'll try and take that inner integral with respect to y. So I'm going to take the antiderivative here, and I should get sine of x plus y. I'm doing a u substitution, but I end up with du just equals dy. And I'm going from y equals 0 to y equals 2x. Sometimes I'll use this notation of y equals 0 to y equals 2x rather than just writing 0 and 2x, just because I think it makes it more clear what you need to plug in for what. Okay, let's go ahead and simplify this. We're going to get, leaving what's on the outside alone, we'll get sine of, looks like 2x plus x, so sine of 3x, minus sine of x plus 0, so sine of x. Now what I want you to notice here is that all of the y's have disappeared. We just have x's left, which is great because we have to do an integral with respect to x in the next step. We'll continue the problem a little bit just so you can see that more clearly. If I simplify this a little bit, you can see that I get sine of 3x minus sine of x dx, and now I just have a single variable calculus problem. Okay, I know I went through that quickly, but I wanted to emphasize that at the end of the day, I really do just end up with a number, right? I integrated all the y's away in the first integral, and then I integrate all of the x's away in the second integral. Now, back to the original problem, we made a choice here to integrate with respect to y on the inside and then x on the outside, but we could have made the opposite choice. We could have decided to integrate with respect to x on the inside and then y on the outside, and I'll go ahead and show at least the setup of how that would work here. So setting up Fubini's theorem once again, the double integral of cosine of x plus y dA ought to be equal to a double integral. This time again I'll be putting y on the outside and x on the inside. Again, I'll be thinking about trying to fill in the 4 blanks here for my limits of integration for x and for y. Now, in general, I actually like to do this in the opposite order that I just did and fill in the blanks for the outer integral first, since they have to be constants. Looking at my picture, I can see that y ranges from 0 to 2. And so I'll fill those in right now. The inner part's the harder part, and I can remember that we're supposed to treat y as a constant inside that inner integral, and because of that I can have y's in my limits of integration for x. Geometrically, setting y equal to a constant means that I'm drawing a horizontal line. And I ought to be thinking about what's the smallest that x can be along that horizontal line segment and the largest that x can be along that horizontal line segment. So looking at that line segment, no matter what y is equal to, the upper limit should always be 1. Right? Even if that y were higher or lower, my upper limit would always be x equals 1. And so I'll fill that in as my upper limit of integration. Now the lower limit is what changes. You can see that for different values of y, I would get different lower limits of integration for x. So this is going to be the limit of integration that depends on y. Now that lower limit of integration is determined by that line y equals 2x, but I'm trying to say what the x value is in terms of y, so I really just need to solve for x in that equation, right, that x equals y over 2. So that lower limit of integration really would just be x equals y over 2, and so I'll write it in that way in my iterated integral. So now if you wanted to, you could go ahead and solve this iterated integral, and you should get the same answer as what we got doing it in the other order. Now, one thing I'll point out here is that these two iterated integrals are kind of different. You wouldn't be able to necessarily come up with the one that we did second from the one that we did first. Looking at the limits of integration, 0 to 1, then 0 to 2x, versus 0 to 2, then y over 2 to 1, it wouldn't be immediately obvious. You sort of needed to draw the picture and look at the picture before you could decide what all those limits of integration were. And yet, even though they are set up quite differently, you should be able to get the same answer going in either order. So normally you do whichever one you find easier. So let me now show you a problem. It's not one that we're going to do today, but just to motivate the problem that we'll do next. This problem is an iterated integral. It's already been set up as an iterated integral for you, but I bet you'd be hard-pressed to actually take this antiderivative with respect to y. It's supposed to be y first, y on the inside, but I don't know the antiderivative of this function. The key here is that if I were to switch the order of integration and integrate with respect to x first, you can probably already see that this is an easier integral with respect to x than it is with respect to y. And it turns out that if you switch the order of integration, this becomes a much easier problem. So with that in mind, you shouldn't necessarily be thinking, oh, well, I like doing y first instead of x first, so I'll always do that. Sometimes you have to do it one order versus the other in order to be able to make the integration feasible. So I'm not actually going to do that problem. I'm going to scroll back to number 5, which gives us an iterated integral, but it wants us to sort of work backwards. First, it wants us to turn this iterated integral into a double integral, so we have to think about what that region R would look like. And then we're going to change it into a new iterated integral in the opposite order, so dx on the inside and dy on the outside. You'll see these problems as like switch the order of integration kinds of problems. And they won't always tell you to do this intermediate step of drawing a picture, but these problems aren't really possible without drawing a picture. You have to draw a picture in order to even get started on them. So I've included those instructions here to get you used to doing so. So to think of this as a double integral, we have to specify what region in the plane we're talking about here. And as I did before, I think it might be helpful to write down this region using inequalities. So when I look at that outer integral, x ranging from -1 to 1, I can think of that as telling me the inequality that -1 is less than or equal to x, which is less than or equal to 1. Likewise, looking at the inner limits of integration, y should go from x squared to 1. That is, x squared is less than or equal to y is less than or equal to 1. And the idea is that by writing it this way, it might give me a better idea of how to draw my picture. So for starters, I know that x is between -1 and 1, and so I'm going to sort of be between these two vertical lines that I'm tracing out with my mouse. Now for y, it should be bounded by x squared on the bottom. So let me draw that. That's going to be the bottom. And then 1 on the top. And so once we sort of piece that together, we can see what our region looks like at least. And so this should be the region R that we're talking about in the plane. So now we can say that this iterated integral can be written as a double integral over this region R that I've just drawn for you. And now the next thing that the problem asks us to do is to rewrite this double integral as an iterated integral, but this time with x on the inside and y on the outside. So let's get started in doing that in a similar way to what we did last time. Y on the outside and x on the inside. And again, I've got to think about sort of filling in 4 separate blanks. My function is not really given to me. It's just a generic f of x, y. And I really just am focused on the limits of integration. So in trying to fill in these 4 blanks, I'll start on the outside just because that's usually simpler. These just have to be numbers. What's the largest value that y can take and the smallest value that y can take? And also bearing in mind that in that inner integral, I'm treating y as constant. So thinking about the outer integral, I can see that y has to be between 0 and 1, between those horizontal lines I just drew. Now in thinking about the limits of integration for x, I have to treat y as a constant. And geometrically, that means drawing a horizontal line. I can see from my picture that the upper and lower limits of integration for y are going to depend on what y is. y is close to 1, then I'm going to have a wider range than if y were close to 0. So I just sort of drew one value of y as a representative so I can sort of see what I'm up against. Both the left and the right sides of this line segment lie along the parabola. And my goal is to see what x is equal to at each of those, the upper and lower ends of that line segment. So the parabola is determined by the equation y equals x squared. But again, I'm trying to write x in terms of y along the parabola. And so I'll solve for x. I'm writing x equals, and I should be careful, plus or minus square root of y. And in fact, it makes sense that I would get two answers here, because on the lower end, you can see that's where x equals negative square root of y, and on the upper end, that's where x equals positive square root of y. And so for a given y, those ought to be my lower and upper limits of integration for x. So I'll often ask questions where I just want you to set up the iterated integral. And what I mean by that is start with a double integral, and you need to tell me the limits of integration. You can see there's nothing to calculate here because I didn't tell you the function f of x, y. And so for this problem, we're sort of finished. However, I have sort of a follow-up question here, which is, can we take advantage of the symmetry here? Is this double integral that I just wrote down really equal to twice the double integral over just 1/2 of the region R? So you can see I've changed it from x going from negative root y to y to x going from 0 to root y. So just to draw what that would look like, now x has to be non-negative. It's only the part on the right side of the y-axis. I'll just draw it real quick. So you might be used to doing this sort of thing in calculus, where we take advantage of symmetries in the function. But there's something I need you to be careful of here. And it comes from the fact that there are really two pieces to this question. There's the region of integration, but there's also the function f of x, y. Thinking about population density, what if the population density is greater on 1/2 of the city than the other? If it's more densely populated on the left side than the right side, for example. In that case, the region might be symmetric, even though the function is not symmetric. And so you have to be careful on questions like this, or if simplifications that you think you can make just based on the region, when really it's the function is not necessarily having the same symmetry that the region is. And so I think our answer here needs to be not necessarily. If we knew what the function were, then maybe we could say a little bit more, but since we don't know the function, we can't rule out the possibility that the function is not symmetric in the same way that the region is. And so we don't think that this is necessarily equal to double the double integral on the left side or right side. Okay, that's it for this lesson. You'll get a lot of practice with this in recitation on Tuesday. So I'll see everybody again on Wednesday.